Hi everybody. We're going to work on Unit 5 today, and in particular we're going to work on simplifying radicals. Before we begin though, if you feel like you need to review how to evaluate square roots and cube roots and radicals in general, then you can go look at page 341 for some review exercises. Okay? Alright, so let's begin with the definition. I'm just going to state what it is. State the definition of a radical so that we can have some vocabulary. So we're all talking the same language. So here's the definition. The nth root of a equals b, where b to the power of n is equal to a. In other words, b times b times b n times equals a. Actually, I'm just going to adjust the light just slightly here. See what happens if I do this and this. Yeah, that looks slightly better. Maybe turn off the LED here. That looks about right. Okay, so we call the n, we call that the index of the radical. Okay, and then the a, we call the a the radicand. Okay, so maybe let's just do a quick example on how to evaluate these. So for example, the fourth root of 16 is equal to 2, since 2 to the power 4 equals 16. Okay, 2 times 2 times 2 times 2 is 16. Good. Okay, I'm going to give you a property here. This is a property, well, it's more a definition, but I'll call it a property. Here's a property that we have. And it's just on how to write a radical in exponent form. So the nth root of a can be written in exponent form like so. This is equal to a to the power of 1 over n, like that. Okay, so for example, eight to the power of 1/3 is equal to, well, the denominator in that exponent is the index of my radical. So this is equal to the cube root of 8, which is just 2. Okay, let's do another property here. And it's kind of using the above property, honestly. Right, assume a is greater than or equal to 0, and n and m are positive integers. We like to state these conditions because honestly, if we don't make these assumptions, sometimes we'll get undefined answers and stuff. So let's assume n and m are positive integers. Then we can do the following. A to the power of m over n, well, this is the same as the nth root of a to the power of m, like that. Or we could also say this, or it's equal to the nth root of a all to the power of m, like that. Okay, and you know, if I were to actually evaluate a numerical expression that had a rational exponent, I would use this one. Okay, but for this chapter, this is the one we want to focus on. Okay? All right, so let's look at an example here. Okay, the fourth root of x to the power of 8. Well, if I want to simplify this, then I can see the index is 4 and my exponent is 8. Therefore, again, the index is always the denominator. So this is equal to x to the power of 8 divided by 4, like so. And then 8 divided by 4 is 2. So this equals x squared. Okay, now the textbook lists another property, and I'm going to mention it. I'm not sure how much I'll use it, honestly, but it mentions this. It just says the nth root of a to the power of n. Well, if you look at this above property here, n is the exponent, and n is the numerator, and n is the index, so it's also the denominator. So this is just equal to a to the power of n divided by n, which is just a to the power of 1, or a. Okay. All right, good. All right, I think we're ready to jump into simplifying radicals here. I'm just going to list one more property, perhaps the most important property of the bunch for this video. And it says this. It says that the nth root of a times b, if I have a product on the inside, if my radicand is a product, I can break this into two radicals, like so. This is equal to the nth root of a times the nth root of b. Okay, and this is what we're going to primarily use in this video. Well, and the ones I just showed you, but this is the main piece. Okay, so this is the idea. Okay, let's simplify the square root of 8. Well, the idea here is we just want to get this as simplified as possible, and to do this we're just going to look for the factors of 8 that are perfect squares, and then evaluate the perfect squares and leave the non-perfect squares inside the square root. So this is equal to, well, I see that 8 is the same as 4 times 2. And then using this property, I can break it into two square roots. Like so. And now I can evaluate the square root of 4. That's just 2. And we still have the square root of 2, so we've got 2 times the square root of 2, which we just write as 2 root 2, like so. Okay, now it's absolutely appropriate to just do this in your head. You just say, okay, 8 is just 4 times 2, square root of 4 is 2, and therefore my answer is 2 root 2. So it's absolutely appropriate to jump from this step straight to the answer. Okay, all right, let's give this another shot. Okay, now the idea here is, okay, this is an exact answer in simplified form. You might consider it to be calculator ready. Okay, all right, so let's try this again. Let's try a couple of them. Okay, for example, let's simplify the square root of 27, and let's do the cube root of 16. Alright, here's the idea again. Well, we're just going to find all the factors of 27 that are perfect squares, break it into 2 square roots, and then evaluate the one that was a perfect square. So hopefully you recognize at this point that the square root of 27, well, 27 is the same as 9 times 3, and then the square root of 9, sorry, we can break that into the square root of 9 times the square root of 3 like so, and you can see I'm already tempted just to jump to the answer here at this point, and hopefully you'll get to that spot as well. And then the square root of 9 is just 3, and we would just write 3 times the square root of 3 as 3 root 3 like so. Okay, now with the cube root, what do you think? Well, with the cube root, we're looking for the factors of 16 that are perfect cubes. So in this case, you can hopefully identify that 16 is the same as 8 times 2. And the reason I wrote it like that is because 8 is a perfect cube, i.e. I can take the cube root of 8. So I can break it into 2 cube roots as follows. And then the cube root of 8 is just 2 times the cube root of 2. Good. Okay, so those are 2 pretty good examples, but maybe I'll do one more with you guys. If you want to pause the video and try it for yourself, I would suggest doing that. Okay, let's try simplifying. Let's do the square root of 75. Oh, simplifying. What am I writing here? Simplifying. No, we're just going to simplify it. Okay, well, again, you can see that this is the same as 25 times 3, and again, I'm just looking for the factors of 75 that are perfect squares in this case. And at this point, you can break it into 2 radicals. I can rewrite it as the square root of 25 times the square root of 3, and then the square root of 25 is just 5 times the square root of 3, and of course we just write 5 root 3 like that, and that's our final answer. Good. Okay, we're going to jump into some tougher questions here, but before we do, I'm gonna just start a new piece of paper here. Okay, let's look at this one here. Okay, example. Now I'm going to give you 2 methods for solving this. Let's simplify the square root. Actually, let's do the cube root. The cube root of y to the power of 7. Okay, well, you know, the textbook would do this as follows. It would break y to the power of 7 into y cubed times y cubed times y. So we've got the cube root of y cubed times y cubed times y. And then it would separate into 3 separate radicals. So I'd write it as the cube root of y cubed times the cube root of y cubed times the cube root of y. Sorry, it's quite late here. It's the only time I could get some quiet time in the house, so. Okay, and now we stated this property on page 1 of today's lesson. We said, well, the nth root of a to the power of n equals a, right? So I've got, if I rewrote this in rational exponent form, this would just be 3 divided by 3, which is just 1. So this is just equal to y times the cube root of y. And then y times y is y squared. And I still have the cube root of y right there. Okay, all right, so that's one approach to this question. Here's my approach to it. Okay, so I mentioned this other exponent rule to you, how to write it in rational form for a reason, and this is why. Well, I could do this. I could rewrite this as the cube root of y to the power of 6 times y. You'll agree that y to the power of 6 times y gives me y to the power of 7. And then I can break it into two radicals as so. Okay, now remember, I said the nth root of a to the power of m is equal to a to the power of m divided by n, like so. Therefore, y to the power of 6 is the same, or sorry, the cube root of y to the power of 6 is the same as y to the power of 6 divided by 3, which is y squared, like that. So therefore, this is just equal to y squared times the cube root of y. Okay? All right, so, I've had a lot of students tell me they prefer this method to this method. That said, I'm going to do this method when I solve these next few questions. And this method, I'm going to use it, but I'm just going to do it in my head. I'm going to show you how I would do it in my head. Okay? All right, so, for example, I might run out of space here, but let's just go for it and see what happens. Okay, let's simplify. The square root of x to the power of 6 times y to the power of 5 times w cubed. Okay, so if I were to do this in my head, I would use this property here personally. And what would I do? Well, I know there's a index of 2 here. Okay, remember, when we do a square root, we don't include the index, but it's known to have an index of 2. So what I do in my head is just say, okay, well, 6 divided by 2 is 3. Right? If I rewrote it in rational form, I would do a 6 divided by 2, which would give me x cubed. And then y to the power of 5, well, 5 divided by 2 is 2 with a remainder of 1. So I'd say, okay, well, this is y squared, and I have 1 left over on the inside of the radical. And because 5 divided by 2 is 2 with a remainder of 1. And then for w cubed, well, 3 divided by 2 is 1 with the remainder of 1 there. Okay, so I'm I hope you can pick up on that. Okay, now this is the alternative method that the textbook would use here. Okay, it would say, well, wait a minute. I'm going to break all of these into their perfect squares. So x to the power of 6 is the same as x squared times x squared times x squared. And then y to the power of 5, if I break that into perfect squares, that would be the same as y squared times y. And then w cubed, that's the same as w squared times w, like that. Okay, now it would break it into a whole bunch of square roots using that property we stated. Oh no, did you see that? Oh boy. Okay. When it rains, it pours, right? Okay, I'm not sure how long this pencil will last, but we'll hopefully get through this question. Okay, so this is equal to the square root of x squared. And I'm just going to break all of these into its own square roots times the square root of x squared times the square root of x squared times the square root of y squared times the square root of y squared times the square root of y. Can't believe it, I'm running out of room again. Get rid of this line once and for all. And then we've got the square root of w squared times the square root of w, like so. Haha. Dull pencils are the best. Times the square root of w, like so. Sorry about that. Okay, now it would begin evaluating all of these. Well, the square root of x squared is just x. Square root of y squared is just y. And then we can't do anything with the square root of y, just leave it as so. And then the square root of w squared is just w. And then the square root of w is just the square root of w. And then it would just reorganize it. X times x times x is x cubed. I shouldn't say it would reorganize it, just do the multiplication. Y times y is y squared. And then we can put the w with the other pieces that don't have a radical. And then here, I can recombine these radicals. By multiplying the radicands together. Okay? Alright, so, I'm not a big fan of that, to be perfectly honest, but it is what it is. Alright, let's try one more example, and then we'll call it a day. Okay, let's simplify. Let's do the square root of, I'm making a big one. Let's do the square root of 32 times x cubed times y minus 3 cubed. Okay, so again, I'm gonna use the books method here. Well, hopefully you can see that 32 is the same as 16 times 2, and then x squared is the same as x squared times x. I'm trying to break these into perfect squares because I'm working with a square root. And then last but not least, I've got y minus 3 squared times y minus 3. All right, now at this point, I'm going to reorder these inside the radical. I think I prefer doing this way if I'm going to use this long method. Okay, I'm going to put all the perfect squares at the front. So I've got 16 x squared times y minus 3 squared times 2 times x times y minus 3. And the reason I'm doing this is because instead of writing all of these out as separate radicals, well, none of these are perfect squares, hence I'm just going to leave them inside. Okay, so I could rewrite this as, so this is equal to the square root of 16 times the square root of x squared times the square root of y minus 3 squared times the square root of, I'm just going to leave all of those inside the radical rather than recombining at the end, 2x times y minus 3, like that. And now we can start evaluating. The square root of 16 is 4. The square root of x squared is x. The square root of y minus 3 all squared is just y minus 3. Don't forget to keep your brackets here. Okay, and then I've got the square root of 2x times y minus 3, like so. Okay, you know what, maybe we'll do one more example. I'm just going to, again, show you how to kind of evaluate these in your head. So I really kind of enjoy doing it this way. Okay, let's do this. One last example, just a mental calculation. Let's do the cube root of x to the power of 8 times w to the power of 10 times z to the power of 5. Okay, so again, using that property, and maybe I'll just write it down here. The nth root of a to the power of m equals a to the power of n divided by m, m divided by n. Using that information, I'm just going to evaluate this in my head. Okay, so I can see the 3, the index is going to be the denominator for everything. So how would I do this? Well, I'd say to myself, x divided by x to the power of 8 divided by 3 is 2 with a remainder of 2. Okay, so in particular, maybe I'll just do this off to the side. You know, x to the power of 8 equals the cube root of x to the power 6 times x squared, and then 6 divided by 3 is 2, and I'd have 2 left over on the inside, because that's not a perfect cube. Okay, so I would get x squared, and then I'm going to have a x left on the inside. I'm sorry, I'm going to have an x squared left on the inside. Okay, so the idea here is I just look for what 10 divided by 3 is, which in this case is 3, with a remainder of 1, right? 3 times 3 is 9, plus 1 is 10. So this would just give me w cubed, right? 10 divided by 3 is 3, with a remainder of 1. And it will take a bit of practice doing this, but I'm sure you'll get pretty comfortable with it pretty fast. And now 5 divided by 3 is 1 with a remainder of 2. Okay, all right, so that's it for this video. We're not quite done these properties yet, so what you can do is do page 351, but don't do any of the ones with fractions. Hope I got that page number right. And don't do any of the ones with fractions. Okay, bye for now.